Hello boys and girls, welcome to another section of our chapter here on polynomials. Today we're continuing to multiply polynomials, but today we focus on not just any old polynomials, any low-life polynomials. Today we focus on the famous ones, the A-list of polynomials. So it goes something like this. We won't do all the super famous ones, we'll just do most of them, and it goes something like this. We'll start off with something famous called the difference of squares. So every time you've got a polynomial that looks like this, x minus y and x plus y, so you have the same item, same two things being multiplied, but one of them is a plus and the other one was a minus. They could look like this, or like this, or like this, or like this. The point is that you have the same two items, and on one side they're being added, and the other side they're being subtracted. Then we can learn this pattern here, and then solve all of them once and for all. So we start off with a basic one and we try to figure out what exactly is the pattern. So we multiply this using our excellent skills here for multiplying. I believe I could do a FOIL here or kindergarten method, whatever. Let's do FOIL. Let's do the kindergarten method. X plus y times x and a negative y, and I'm going to be multiplying these. So I'll get negative y squared here, and I'll get negative xy here. Here I'll get positive xy. And here I'll get x squared. So when I add them together, I get a total of x squared, 0 there, minus y squared. This is the kindergarten method. And that shows you that every time you have the same two items on one side being added, on the other side being subtracted, and you're multiplying them, you get the first item squares, and then the last item squared with a subtraction. Or said differently, if you foil these, here's another way to do it. If you foil this, the O and the I turn out to be opposites of each other, and they go away. Okay, that's a very special case when you have difference of, this is difference of squares. This is why it's called the difference of squares. You have a square minus another square, the difference of squares. You can go both ways. X squared minus y squared, well, that's x minus y, x plus y. Or you can go the other way. The other way, if you have x minus y times x plus y, clearly that would be x squared minus y squared, difference of squares. Okay, so once you got that under your belt here, maybe you should do some flashcards or some knapsacks or something to make it very comfortable for you. This is an easy fact to prove and to learn. Then you can go on and apply it here. So the difference of squares would say, oh, I have the same item here, same item there, one here subtracted, here added, so therefore it's the difference of squares. 5 squared minus 2 squared. That's by difference of squares. And then you're done. And then you can play a little game here to see if it makes sense with other notions that you may have. Other notions that you may have would be like 5 minus 2 is 3, and 5 plus 2 is 7, so this should be 3 times 7, which is, of course, 21. The difference of squares says no, that's 25 minus 4. Oh, that's also 21. You see why they pay me insane amounts of money? Difference of squares. Alright, and you think symbolically about it. It doesn't matter what these things are. This could be blah, any sort of blah. This could be any sort of stuff. The answer, of course, would be triangle square minus that one square by difference of squares. Okay, this is a nice abstract way of looking at it to make it more powerful, to see that it applies to everything. Everything. Triangles, squares, circles, everything. Almost everything. Maybe there's some places where it doesn't, I don't know. Certainly if it's in a place where our rules apply, like the distributive law and all those things, then it worked there. Triangle square minus this square, done. Difference of squares. Can't believe I get paid to do this. Here, this one would be x squared minus 3 squared. Difference of squares, done. You could take it one step further if you wanted to. Hide the pattern. If you want to be a pattern hider, you could turn it into that. X plus 5, x minus 5, that would be x squared minus 5 squared by difference of squares. Done. My God, this is too easy. How about this one? You have, when the first term has a couple things in it, well, it doesn't matter. You still have 2x, but you have to put it in parentheses here. Square, that item square, minus the other one square by difference of squares. And so you could clean it up some more. This is 2 times x times 2 times x. That'll give you a total of 4x squared minus 1. if you wanted to hide the patterns. Alright, this one would be 2x squared minus 3 squared, difference of squares. So that will give you a total of 4x squared minus 9. Easy, right? You could have other degrees, degree 3 and degree 3. Doesn't matter, as long as these two match and these two match, and one's a plus and one's a minus. It's perfect candidate for difference of squares. So this would be x third squared minus 1 square, difference of squares. Of course, this is x to the third times x to the third. So that's xxx times xxx. That's a total of 6 x's minus 1. Alright, pretty easy, right? Difference of squares. Let's go on, and how about difference of cubes? Alright, let's do a difference of cubes. If it's the first time you ever see this, let me give you some pointers here to try to spot them. Here you just have the difference, x minus y, and on the other side you have a bunch of x's and y's, but there's a certain pattern to the madness here. Look at the number of x's. You have 2 x's first, and then 1 x, and then no x's. So they decrease from 2 to 1 to 0 on the number of x's. Look at the number of y's. You have 0, 1, 2. They increase the number of y's. So one of them is going down, the other one's going up. That's the perfect pattern for difference of cubes. So again, if you're a beginner and you've never done this before, you might try doing it something like kindergarten method. How about this? X squared plus xy plus y squared times x plus negative y. Let's do some kg on this baby. That one would give you negative y to the third. That one would give you xy squared with a negative. This one would give you x squared y with a negative. That's these two. And I'm done with that. Now I go with the x's. That was that one times that one, that one times that one, that one times that one. Right? Now I do the x's. I'm going to do x times that, x times that, x times that. So x times that would give you xy squared. X times that would give you x squared y. X times that would give you x to the third. And now I add them. So I would get x to the third. These two are opposites of each other, so they give you 0. These two are opposites because they give you 0, so they give you 0. And all you're left with is the difference of cubes. I told you. So here's something famous for you. Every time you have a cubed minus another cube, the difference of cubes, you should think that's the multiplication of a famous couple of polynomials. The number of x squared, x's decrease, the number of y's increase. Just like that. Famous, famous, famous difference of cubes. Okay. Not only that, but you could extend this difference of anything. If I had x to the 5 minus y to the 5, you could play the same game. This would be x minus y, and then the number of x's decrease, starting with 4, 3, 2, 1, and no x's, and the number of y's would increase. No y's, 1 y, 2 y's, 3 y's, 4 y's. Right? So you can't see that. Too bad. You gotta pay extra if you want to see that. Alright, anyways, no, I'll do it here. Let me think. Yeah, I'll do the one for 4 right here. X to the 4th minus y to the 4th. First you do x minus y, and then you put the rest of it here. 3 x's, 2 x's, 1 x, and no x's. Number of y's, no y's, 1 y, 2 y's, and 3 y's. And that's how you do it. These are super famous. Again, if you want to see why, you should try the kindergarten method like we did here. And so you should put that in your brain somewhere where you have a drawer for all the famous stuff, for all the famous polynomials. A drawer in your brain. So then let me think. So then problems may look something like this. Here, check the pattern here. You got this guy squared, that guy square. The number of triangles decreases, the number of squares increases, and you have the difference over here. That's a perfect candidate. That is triangle cubed minus square cubed by difference of cubes. And you're done. Or you could do it the long way if you want. Pretty nice, huh? Same thing here. 2x, the quantity squared. The number of 2x's decreases, the number of 1's increase, and you have the difference over here. So this would be 2x to the third minus 1 to the third by difference of cubes. And you could simplify that if you want. 2x times 2x times 2x. That would be that if you want to be a pattern hider. This doesn't hide the patterns, this hides the pattern. Difference of cubes, easy. By the way, I want to show you something interesting. What would happen, this is true for no matter what triangle is. Triangle could be anything, blah. This one could be some other thing. Some other thing. Anything would work here. Well, as long as it's part of the real numbers, the things that our axioms apply to, then you could, you know, everything, the whole world is open. Anything where our axioms apply, you could plug them in there. In particular, what would happen if I substitute triangle is equal to x, and I substitute square is equal to 1. If it's true for everything, it's certainly true when this is the case. So if I substitute that, I would get that x minus 1. What I'm doing here is everywhere I see a triangle, I would substitute an x. And everywhere I see a square, I will substitute a 1. So this will be x squared plus x times 1 plus 1 squared. This will be a certain case of the difference of cubes. But wait, this becomes x minus 1 times x squared plus x plus 1. And this becomes another super famous. This is called the geometric polynomial number 3. This guy is equal to x to the third minus 1 to the third, of course, which is x to the third minus 1. Because I knew that this one was equal to the triangle to the cubed minus square to the cube. So I substitute x to the cube is that, and what the square to the cube is that. This becomes something famous, and so every time you have, for example, something like this, x cubed minus 1, you should think, oh, that's x minus 1 times x squared plus x plus 1. And in disguise, what that is just a special case of the thing you already learned, the difference of cubes, where the first item is an x and the second item is a 1. And there's more to that. Just like there was the difference of fifth powers, there's also the x to the 5 minus 1. So that one would look something like this, x to the 5 minus 1. It would look like x minus 1, and then the number of x's decreases, 4, 3, 2, 1, and the number of 1's increase. But you don't even need to put the 1 there, because 1 doesn't do anything, so all you have is a 1 at the end. 1 to the 4th if you want to be pedantic about it. Some nice stuff here happens, and this is a family of other super famous. This will be called geometric series polynomial number 5. This is number 3. This gives rise to another family of famous polynomials, which are really just those same ones in disguise. Okay, and the other thing I want to say, if you ever are stuck and you have no idea, you could just multiply it out yourself. If you don't know what x minus 1 times x squared plus x plus 1 is, well, then you can use kindergarten method and do it for yourself so that you own it, and you'll see what it is. Okay, some nice stuff here.